I've got Livia. I think we're only missing one. All righty. So today there is no warm-up. We are working on algorithms, unreasonable time. We're doing U6 L3 to 4 activity guides. That is due Monday the 19th. Your create performance task you are still working on. You need to get the video, your program code PDF, your written code PDF responses submitted to the College Board in the AP digital portfolio by May 14th. That's when we will check them. Okay, our goal or objective today is that you will be able to explain the differences between problems that run in a reasonable time and those that do not. Explain how both formal mathematical reasoning and informal measurements can be used to determine an algorithm's efficiency. Determine if an algorithm runs in an unreasonable time and develop heuristics. Okay, I want to show you the worksheets because we've had a little trouble with them today. Okay, so let me go into our module. There we go. Come on. Get back to, there we go. Okay. No, I don't need to be there. Sorry about that. In here is your U6, L3, and L4 worksheets. We've had some trouble with permissions on these. Oh, look, there's Olivia. You're already here. Traditionally, we have issues with Google assignments with permissions. I had difficulty getting them out of here, this Unit 6, Lesson 3, Unit 6, Lesson 4. I was able to get them out of this link in the assignment. I can get a copy of L3, and then I go back here and I can make a copy, I can get L4. You need to make a copy so that you can write in it. And Google Docs was down this morning. So is everyone able to access your U6L3 and your U6L4 worksheets?
No, I was having some trouble with it.
Okay, I'm going to put a link into the chat. It's something that everyone has had difficulty with today. Okay, so let me go to...
Is this for fourth quarter or this is also for third quarter assignment?
Technically, this is fourth quarter. You are
Okay.
brilliant. It's due Monday. Quarter ends on the 16th. So this is not for this quarter. Hang on. So here's L3, and I believe I have it sharing totally open. Yes. All right. Okay, so U6, L3. Okay, try that. That should work. It worked for the other class.
Yeah, it worked.
Okay, and here comes L4. Hang on. You turn it into the assignment. In theory, there are two. In theory, you should be able to upload them. You should be able to upload them both in this Google assignment. Let me know if you're having issues with it. As I say, I have nothing but trouble with Google assignments. Usually they are not a problem for turning things in though. So I would guess you should have a submit button somewhere on that. Here, I can look at student view. Oh, you've got to link your account. I seem to have a bunch submitted, which is a little strange. But I'm not seeing a submit. Anyway, it should be there. Let me know if you're having trouble. I always get lost when I'm looking on the student side. Reset, leave student. Okay. Oh, look, there's Eric. Welcome, Eric. All right, we're just getting started. One thing you need to do. Oh, shoot, you just came in, so you're not going to be able to get them. Hang on. I'm going to put, these are our worksheets, and everyone's had trouble accessing them. So U6L4 should be, check the chat. That should be U6L4, and let me do U6L3 worksheet. Let me get it. Not 4. All right, so you should be able to access those, Eric. Back to our lecture. Everybody okay? Everyone following along? It's a bit of a crazy day. Don't ask me why. All right, this is just the project progress checks. Your topic is selected and you have given me your topic and one sentence about it. Progress check 2 is just the idea that you have something on your design mode. A button. You've changed it from screen 1 to start screen. That's all I need. I am still missing about 30% of my students' work. I am not seeing anything in your code.org, and I am not seeing a written description of your app or how it's going to work. For the code.org, I am guessing you guys are working in App Lab. If so, you need to send me a link. I know some people were asking, oh, gee, I'm working with a partner. Can we only submit once? That's great, but you got to tell me who your partner is. Nobody has told me who a partner is. So just what I'm worried about is if you have not come up with an idea and are having difficulty. If you have not come up with an idea and are having difficulty, reach out to me. I will help you. We even have students that can help you. All right? Get me your stuff. These are easy points, okay? I shouldn't be missing. Here's today's warm-up. What does it mean to say one algorithm is more efficient than another? And we're going to put this in the chat, or you can sing out. What does it mean to say one algorithm is more efficient than another? Jordan says that one algorithm works better than another. They do the same thing, but the more efficient one has less code. Technically, I would say that is an interesting assessment. It's really about the time it takes to get the answer. Run smoothly with the least amount of code. Does it mean that it has less lines of code and is still functional? Efficient is doing more with less code. For this purpose, efficient is about processing the data faster. So it's the idea that it processes whatever it is you're doing faster while still maintaining accuracy, right? It does its job more effectively. I agree, everyone thinking that less lines of code is more efficient or effective in terms of coding, but that's not what we're talking about here. Here for algorithms, it's really about how fast you get, your algorithm produces an answer, okay? I should have written down, I had a great answer from one student. It's just that idea that it is, processing the information more quickly while still maintaining its accuracy. All right, lesson 3, unreasonable time. What is that? The pair raffle. The winners are any 2 tickets that add to the winning number. First thing we're going to do, you've got your activity guide. This is the U3. Complete that before continuing this slideshow because it won't make any sense. Okay, let's go to our activity guide. All right, so I'm going to go to U6L3. Hey, there I am. Open up the ticket generator widget on code.org. I can do that from right here. This is Unit 6, Lesson 2, Circle 2. Okay, click Run to start the app. Click Get a Ticket to generate a random ticket number. So the first thing I'm going to do is generate 1 ticket, 389. I come back to my worksheet and it says, generate a raffle ticket number for yourself. Record it here, right? What was my number? 389. Okay, I can type that right in here, but I don't want you downloading mine. So then generate 10 more raffle ticket numbers, record each number below. So just go to your app, crank out 10 numbers and write them down in that box. That's all you're doing, okay? I'll give you a minute to write down your numbers. Okay, so now it's saying challenge 1, the pair raffle. You win if your raffle ticket number combined with one of the other 10 raffle ticket numbers adds to the winning number. The winning number is 1,000, okay? See if you have a winning number, a winning pair, and record your results here, all right? That's pretty straightforward. So my number was like 387, and then I'd have, 582, 691, 34, 583, 921, whatever. Do any of those add up to 1,000? Okay, for the group raffle, challenge 2. If we were in school, we could do this as a class, but since we aren't, think about how this could be done. You win if your raffle ticket number combined with any other 10 raffle ticket numbers from 1 ticket up to all of them add up to the winning number. The winning number is 2,500. See if you're part of a winning group. Record your results here. Okay, I'll give you a moment to look through that. You are generating your ticket numbers from your ticket number generator right here. You're just clicking get a ticket to get the numbers. You are not making these numbers up. Okay. All right, so the big question is, which raffle felt like it was more difficult to check and why? Let's pick on my friend Jordan. Jordan, which raffle do you think would be more difficult to check and why? Any ideas? Jordan? All right, I don't want to pick on my friend Ken Gao. Who am I going to pick on? Nikolai, my friend Nikolai Forrest. Which raffle felt like it was more difficult to check and why? Can you take a guess at that or give me the answer?
My
There we
guess
go.
is the first, but I'm unsure why.
Okay. Well, Jordan has come to your rescue.
Thank
She
you,
is
Jordan.
thinking it's the group, not the. Think about this. In the first raffle, we had 1,000 numbers to go through, and all we had to do was find 2 tickets that could make that number. Think of how many things we'd have to check to do that. In the group raffle, I have 2,500 numbers, and I have 11 different tickets per person that I can make a combination out of to try and win my raffle. So I am going to have to check a whole lot more combinations of tickets doing the group raffle than I am with 2,500 than I am with the individual. Hello, AP CSP. What's your name? Oh, hello. You're Hugo Cristobal, or no? Okay. All right, please, just come on in and just work off your laptop. So you're just supposed to be at least a computer away from each other. A common question. Hugo, are you sure you're in the right class? This is Mr. Swift's. What? Okay, but what's your last name? Oh. I don't have a Morales in this class. I don't have anyone with an M. Here, do you want to just help me? No worries. Bye. Well, we've had our first wrong student. Okay. The idea is that it's just a lot more complexity when you're dealing with multiple tickets and a bigger number. Okay? We could write an algorithm that goes through every possible check for the pair raffle or the group raffle. Let's see how many checks there are. Fill in the 2 tables on the next page. Okay, so for the pair raffle, every participant gets a random ticket. A winning number is chosen, also at random. The problem is to determine if any pair of tickets adds up to the winning numbers, right? So here's our example. The tickets 108, 442, 913, and 5, and a target number of 500. This instance does not have a winning pair. The tickets 250, 20, and 4, and the target number is 254. This instance does have a winning pair, 250 and 4. How many checks? Fill in the table below with how many checks. I think I've already filled something in there by mistake. Fill in the table below with how many checks are necessary with different numbers of tickets. It may help to draw pictures and see if you start noticing any patterns that emerge. Okay, so you may need scratch paper. You're trying to see how many checks do you need to see if you've won the lottery. All right, this is pairs. If you had 3 tickets, how many checks would it be? If you had 4 tickets, how many ways could you check that 2 of your tickets added up to something? All right, for the group raffle, for the for the group raffle, every participant gets a random ticket. I apologize, there are typos in this. The group raffle sounds like it's talking about the pairs. It's supposed to be group. For the group raffle, every participant gets a random ticket. A winning number is chosen, also at random. The problem is to determine if any combination of your tickets, not any pair, add up to the winning number. You can use all your tickets to add up to the winning number. So the tickets 411, 220, 710, and 41, and a winning number of 1,000. This instance does not have a winning group. The tickets 110, 923, 475, 301, and 102. And the winning number is 1500. This instance does have a winning group. 923, 475, and 101 is 1500. How many checks? Fill in the table below with how many checks are necessary with different numbers of tickets. It may help to draw pictures and see if you are noticing any patterns emerge. I can give you one word for that. Think binary, binary, okay? So do your best. Try and fill in how many checks you think it would take to have 2 tickets, 3 tickets, 4 tickets, 5 tickets, and 8 tickets with a group versus same thing with a pair raffle. Okay, I'm going to give everyone another 2 minutes to work on this and fill it out, and then we're going to watch a little video that's going to explain it all. One thing to know, today is actually set up as an asynchronous class because tomorrow is the SATs. So there's a lot of repetition. You will see that the video is going to tell us all the answers, and then we're going to go through all the answers again. This is because as an asynchronous class, we thought it would be easier to get the video up front to understand what you're doing than to have it at the end to confirm what you did. Okay, let's find out what is going on here. All right. Here's our friend.
Welcome to Unit 6, Lesson 3, a reasonable time. Now that your activity guide for the pair and group raffle are complete, let's see how you did. So for the pair raffle, here's what you should have had. But now let's understand why. If 2 people have tickets, you only need to make 1 check between the 2 to see if they add up to what you need. That makes sense. If 3 people have tickets, let's name them Alice, Bob, and you. You would need to check your ticket with Alice, your ticket with Bob, and then Alice and Bob need to check their tickets together. That makes 3 checks. If 4 people have tickets, you, Alice, Bob, and Charlie, you would need to check your ticket with Alice, your ticket with Bob, that's 2 so far. You need to check your ticket with Charlie, that's 3. Alice needs to check her ticket with Bob, that's 4. She also needs to check her ticket with Charlie, that's 5. At this point, the only person Bob hasn't checked his ticket with is Charlie. So that makes 6. And now Charlie's checked his ticket with everyone, so we're done. The exact formula for this relationship, which is actually telling you the highest number of possible checks or highest combinations that you would need to do, is n squared minus n divided by 2. N is the number of tickets that have been distributed and need to be checked. 2 is the exponent because that's the number of tickets that need to be combined in order to get a winning number. We're looking for a pair of tickets. So again, this is going to tell us the highest number of checks that we may need to do. We could get lucky and we could find a winning number on the second check. In any event, you don't need to know the formula n squared minus n divided by 2, but you should know that because of the n squared term, the graph curves up. Any algorithm that includes an n squared or n to the third or n to the fourth or so on is called a polynomial, which means many numbers. Now let's take a look at the group raffle results. And again, let's break this chart down. So remember, with the group raffle, you could combine your ticket with any number of other tickets, or even no other tickets, to get the winning number. Could just be your ticket was the winning number. So you should have seen that was going to be a lot of combinations, right? If just 2 people had tickets, you and Alice, you would need 3 checks to see if any combination of those 3 tickets made the winning number. Your ticket by itself, Alice's ticket by itself, or yours and Alice's tickets combined. That's 3 checks. If 3 people had tickets, again, you, Alice, and Bob, it could be your ticket by itself, Alice's ticket by itself, or Bob's ticket by itself. So there's 3 checks so far. You'd also have to check your ticket with Alice and your ticket with Bob. That's 2 more checks. We're up to 5. Alice has to check her ticket with Bob. That's 6. And then we have to check all 3 tickets combined. There's our 7. Again, we could get lucky and find the winning number on the first or second combination, but this exact formula for this relationship, which like the last one, is just going to tell us the largest possible combination. The exact formula is 2 to the n minus 1. N, again, is the number of tickets that have been distributed and need to be checked. 2 is the base this time because you will have 2 possible results after combining the tickets, a winning number or not a winning number. Again, you don't need to know that formula, but you should know that because of the 2 to the n term, the graph curves up very quickly. Any algorithm that includes a 2 to the n or 3 to the n or 4 to the n and so on is called exponential. I want to point one thing out. If we look at this chart here, it just might look familiar to you. Here's another way to look at the group raffle results. This is the exact same chart results we were looking at for the group raffle and the exponential graph a moment ago. And this kind of makes sense since 2 was the base and there were 2 options, winning ticket and not winning ticket. And the number of checks is, again, the highest number of combinations we would have to make, or as we see here in binary, the largest number that we can make with a certain number of bits. Why does everything always lead back to binary? So here's another graph of not only the exponential curve and the polynomial curve, but also a couple others just for comparison. Take a second and think, why might the exponential curve be considered unreasonable? Well, as we can see here, exponential curves grow extremely quickly. You simply can't build a computer fast enough, even for relatively small raffle sizes. Let me give you an example. If we had 100 tickets, following that formula, there would have to be 127 followed by 28 zeros. So I don't know what number that is. 1270000000000 28 zeros. If we built a computer that checks 100 billion combinations every second, it would still take 400 billion years to check all of the combinations. I think we might call that unreasonable. Here's that same graph in a chart, and as you can see, polynomial isn't bad, but exponential gets unreasonably large extremely quickly. So the group raffle is just one example of an algorithm that's unreasonable. It grows exponentially, so we'd never want to run it at our school. Next lesson, we'll talk more about what to do when we encounter unreasonable problems. See ya.
All right.
Welcome to Unit 6.
Come on. All right. So now we're going to go back through it. As I say, it will feel a little repetitive. So which raffle felt like it was more difficult to check and why? Someone want to put that up in the chat? My friend Lily Kreindler already gave me the right answer, but I want to make sure everyone is getting this. So which one was more difficult? Was it the group or the pair? You can sing out. The group, my friend Jordan, taking the lead. You are correct. We could write an algorithm that goes through every possible check for the pair raffle or the group raffle. Let's see how many checks there are. So for the pair raffle, it's the idea that with 2 tickets, there's 1, 3 tickets, there's 3, 4 is 4, 5 is 10, 8 is 28. Not terrible, okay? Again, the idea that, it is the exact formula for this relationship is n squared minus n divided by 2. You don't need to know the formula, but you should know that because of n squared, in the graph, it curves up. Any algorithm whose efficiency includes an n squared, an n cubed, and n to the 4th is called a polynomial. A polynomial. Okay, with the group raffle, the exact formula for that one is 2 to the n minus 1. You don't need to know the formula, but you do need to know that because of 2 to the n, the term the graph, the term the graph curves up very quickly. Any algorithm whose efficiency includes a number to a power, 2 to the n, 3 to the n, 4 to the n, is called an exponential. Okay? There is another way of thinking about this. Binary. Binary. The number of checks is the largest you can make with that many bits. 1 bit, 1 answer. 2 bits, 3 answers. 3 bits, 15 answers, right? 16, but there is a 0 in there. 8, 255, look familiar, right? Polynomial and exponentials both curve up. Why do you think only exponential is considered unreasonable? Anybody have an answer for that? Why is only exponential considered unreasonable? Polynomials seem to go up pretty fast. Okay, because the number's too high, goes on for too long a time, it grows the fastest. It is the most extreme of these 4 cases. Exponential is nearly vertical. Polynomial is about 70 degrees. It's not that bad. Linear is a 1-to-1. This is 45 degrees. And the log or sorted raffle is even lower. It looks like around 25, something like that. So it's this one that is going nearly straight up that is a problem, because the numbers get out of control. This is my favorite, okay? So let's look, in the normal sorted, it's pretty simple. 10 tickets, 4 checks. 20 tickets, 5 checks. In a pair raffle, it's still a lot, but not terrible. 10 tickets, 100 checks. 20 tickets, 400. 100 tickets, 10,000 checks. That's a heck of a lot, but where the polynomial hits 1,000,000 checks on 1,000, the exponential group raffle is 1.07 times 10 to the 301st. This is my favorite notation. At this point, there are more checks than atoms in the universe. Atoms in the universe. My God, there are a lot of atoms in the universe. So that is definitely out of control. It is unreasonable, okay? We should not be having to calculate the number of atoms in the universe to get the answer to our problem. Again, we'll be here for a good long time. Okay, reasonable time. Algorithms with a polynomial efficiency or lower. That means that they are constant, linear, square, cube, etc., are said to run in a reasonable amount of time. The only one that is unreasonable is the algorithm with exponential or factorial efficiencies. They are examples of algorithms that run in an unreasonable amount of time. Okay? In the chat, and I got a perfect match to my previous class last time, so I'm counting on you. Your school is considering running the group raffle at an upcoming assembly to give away a prize. What advice would you give them? Okay, so in assembly, everyone's going to get 10 tickets, and you're going to need to figure out who won up at the dais. And how many students do we have at Churchill? 1,000? What is your advice on running a group raffle at Churchill? Come on, guys. We just went through the whole thing. Do you want to count the number of atoms in the universe? Is that what you're telling me? What? I need someone in the, yes, you're brilliant, Andrew. That is exactly what every class before you has said. Don't do it. Do not do a group raffle. You will never figure out who got the prize. Okay? You want a simple one-to-one. Your number matches this number. Not that you could add 10 numbers together to get the right total. Brilliant. I'm so happy. That's a clean sweep. Every single class. What? Why is this? It's really weird. It's asking me for a password in the middle of my presentation. Oh, come on. All right, we don't know why this is doing this, but there we go. Okay, so now we are going into lesson 4, the limits of algorithms, okay? You want your U6L4. We're just gonna look at the start of this video.
Welcome to lesson 4, the limits of algorithms. So today, we're going to be exploring something called the traveling salesman problem. So the first question I have for you is, how many different paths can you find to visit all of your friends' houses, your house being the one in the bottom left, the green one? So what I want you to do is you're going to pause this video and open up the activity guide that goes along with this lesson and complete the first part, part 1. There are some rules, as you can see. So you must start and end at your house, the green one in the bottom left, and you can only visit each house once. You may need some scratch paper in order to draw all the different paths, but go ahead and pause, go try out that problem, and then come on back.
All right, we are pausing. Is this 4? Where's 4? There's 4. Okay, so here we are, part 1. How many different paths can you find to visit all of your friends' homes? You start and end at your own house, bottom left. You can only visit each house once, all right? Yeah, I think everyone probably has an answer.
Welcome to lesson
Hang on.
4, the limits of distance. These 3 that you could have come up with. You may have similar ones, and you probably... Welcome back. So here's just a few of the multiple paths that you could have come up with. You may have similar ones, and you probably have more than what I've got here. But what do we need to know to determine the best path? So think for a moment on that question. Looking at just these 3 paths on the screen, how do we know which one's the best or the quickest? What do we need to know? If you said distance, you're right. If we know the distance between each house, we can make a better decision about which path to take. So in this example, with the distance being 1 to get to each house, unless you're going diagonal, then the distance is 2. The first option is going to be the shortest. So that's the path we would choose. But what if we had a lot more places to visit? How would we determine the best path this time? Basically, we need to explore all the possible paths in order to determine which one is best. This is what's known as the traveling salesman problem. For each new place to visit, the number of options for possible paths increases factorially. The factorial function is written with the letter n followed by an exclamation point. Here's how factorial works. We multiply all whole numbers from the given number down to 1. So for example, if we have 3 houses to visit, it's 3 times 2 times 1. If there's 4 houses to visit, it's 4 times 3 times 2 times 1, which gives us 24. So that very first prompt that you answered, if you found 24 different paths to take, you're spot on. If there's 7 houses to take, it's 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 5,040. If we look at this graph, with 10 houses to visit, it's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which comes out to over 3 million. That's a lot of possible paths to check for only 10 houses. But let's see how this actually works. So the chart says that if there's 2 houses, there's 2 possible paths. So let's see how we can have 2 possible paths. So let's just say we have a house here and a house here. The 2 paths are there, going from one house to the other, or the second house there. So there's your 2 paths. So it's when you have 2 houses, it's a little bit different than the rules that you had to follow when you had 4 houses, where you had to start and end at the same house. So that's a little bit different when you have 2 houses, but let's look at 3 houses. So if we have 3 houses according to the chart, it says we should have 6 possible paths. So let's see. There's 1 path. I'll just keep a tally mark here. And we can basically start at the same house, but go the other direction. There's our second path. And basically going to do the same thing, but starting and ending at each different house. So there's our 3rd path. And we're going to start at this house, but go the other direction. So the 4th path. There's our 5th path. There's our 6th path. 3 houses, we have 6 paths. Now 4 houses, that was your prompt earlier in this video. And according to this chart, we should have 24 different paths. If you didn't quite find all 24, that's okay. But here's what they all would look like. So hopefully you can see that with each new house that we add, the number of potential paths that have to be checked expands very quickly. The traveling salesman is an optimization problem. It's not a decision problem. We know there is a path. We just need to determine which path is the shortest or most efficient path to take. The traveling salesman problem can be solved with an algorithm which checks each possible option, but it would take massive amounts of computing power to compare every single option, especially as the number of homes to visit, otherwise known as nodes, increases. Therefore, it would take an unreasonable amount of time for the solution to be calculated for most instances of the problem. So in cases like that, where we have an unreasonable problem that we have to solve, we use a problem-solving process called a heuristic. A heuristic provides a good enough solution to a problem when the actual solution is impractical or impossible. For example, think of Google Maps. When you ask Google Maps to give you a path from your home to the mall, there are thousands of different possible routes up every different possible street, many different situations with stoplights, whether they're green or yellow or red. There are so many different paths that you could possibly take. Google Maps goes through a heuristic algorithm and gives you the best possible solution at that time, something that's good enough. So what you're going to do now is pause this video and you're going to go back into your worksheet and complete parts 2 and 3. Parts 2 and 3, you will need to access Code Studio. There are links in the activity guide to take you there, along with the directions. But basically, you're going to make a plan or a heuristic for choosing a good path between multiple different houses or multiple different nodes or dots that you'll see on the screen. So try and think about what would be the best option, a good possible solution or a plan, a good possible plan for deciding which house to go to next in order to find the best distance. When you're done with parts 2 and 3, go ahead and come on back to this video.
Okay. Here we are, part 2. Navigate to level 2 on code.org and try the best path to visit all nodes. Try to find the best path. Write down a plan or heuristic for choosing a good path below. Okay, so if you click here, level 2, it's going to take you to code.org. And here is your app. Click run to start the app, click the nodes to create a path. Try and find the best path to visit all the nodes and return back home. Write down a plan or heuristic for choosing a good path. Note, your heuristic may not always find the best path, but it should be close enough. Okay? Let's read what 2 is for the moment. All right? So 3 then is navigate to level 3 on code.org. Test your heuristic on 3 different levels. Write down the distance for the path your heuristic finds in the table below. Then try and find the best version not using the heuristic. That's called brute force when you're just doing it. Record the distance to the table. Can you find a better path using brute force? Is your heuristic on average pretty good? Should you update your heuristic? Okay, let's take 5 minutes. Okay, so I'll check in about 3 minutes and see if people need more time. Let's work on these 2 parts. First one is try to find the best path and write a heuristic for choosing a good path. In the next one, you're going to test that heuristic against you just trying to find a path 3 times and see which one gets the path done in fewer steps or distances. When you go into your app, out of here, you will see it allows you to, when I run the app, it gives me a number. I can see that 113 is closer than 114 and certainly closer than 121. You can see the distances. So try it out. Okay, as people, I'm getting some questions here. For our heuristic, do we write our total or the number to navigate the total? We'll talk about this when we come back together. Basically, a heuristic is just a strategy. That's all it is. I'm going to go to the closest dot. I am going to go to every dot on the perimeter and then work my way in a spiral. I am going to connect these dots to create a polygon that has nothing in the middle, that the lines never cross. Those are all heuristics. Those are commands that would allow you to connect all the dots back to you again in some fashion, right? All right, so let's go back to the sheet. And let's see what we're getting here, all right? Can someone, for part 2, tell me what their heuristic was? Did you create a heuristic in part 2? Anyone? Can we put this in the chat or you can sing out? Tell me your heuristic. I just gave you some good advice. All right, I'm going to pick on my friend Alexander Wong. Alexander, can you tell me what a heuristic would be to connect our nodes? Alex, you out there? All right, we're hoping his mic is not working. Ali Asher, can you tell me a heuristic that would connect the dots? All it is a strategy. Ali?
Like you have like this, like the smallest amount, so it wouldn't like take as long.
Well, the smallest amount is going to be the closest. All right, so that is a perfect heuristic. I am going to connect to every dot that is closest to me. Okay, so when we go in here, all we're going to do, not the ticket master, I'm going to go, okay, 113, then 78 or 83, I'm going to 78, 67 or 80, I'm going to 67, 93 or 87, I'm going to 87, 137 or 168. I'm just going to the closest dot. All right, that's what I'm doing. That's how I'm going to make this work. And then I'm going to go back to here. All right, that's all we're saying. Okay, so can anyone think up what another heuristic might be? If I'm not
circling clockwise or counterclockwise works way better than this one.
Perfect. Doesn't matter. So you're saying go clockwise around. So it's a little weird, but let's go, here, here. This is almost like the polynomial that doesn't cross. Beautiful. 196 or 1196. That is all a heuristic is. It is just a strategy for accomplishing the goal that you're trying to do. Going farthest from the points. You could do that. All right. So if we go back into our worksheet, navigate to level 3 on Code Studio, test your heuristic on 3 different levels. Write down the distances for the path your heuristic finds in the table below. Then try and find the best version not using a heuristic. That is called brute force. Record the distance in the table. Can you find a better path using brute force? Was anyone able to do this? I think sharing is now on. Does anyone have this that they could show me what their table looks like? I guess technically I can't be sharing. Anyone have a table to show me? Okay, we just saw how to do a heuristic, right? So what did I get in there? I got 1196, okay? So I'm putting 1196 in here. And then I'm gonna go in here and I'm gonna do it with brute force. I think that if I go to the closest one, I'm going to be able to do better. $13.17, that's no good. Okay, so $13.17. Is that better or worse? let's try. Well, class is about to end, so I don't want to do this again. The idea is typically your heuristic is pretty dang good. So our heuristic was much better than my brute force. So the way it worked out last time was typically your heuristic is landing within 1 to 2% of your brute force. That I had people who could do better with brute force, but it's not by much. Think about that. Is getting a 98 on a test a great score? It's just about perfect. It's not really perfect. And personally, I see this in my series. Sometimes I'm on a route that I'm like, I don't think this was the best choice. And that's what they're saying. They are not calculating the perfect choice every time. They are calculating the best choice, whatever seems like the right one, but they are only choosing from 10 routes. They are not choosing from 1,000 routes, okay? So the last thing we need to do is your reflection. Let's just finish up that video and we are out of here.
Welcome to lesson 4.
No. Come on, what's your end?
Welcome to
Here she
2
is.
and 3. Go ahead and come on back to this video. Welcome back.
Yep.
So the traveling salesman problem is, again, an optimization problem. We are attempting to find the best path. It's also an unreasonable problem because there's not an algorithm that can solve the problem in a reasonable amount of time. We need to use a heuristic to come up with a solution that's good enough for most instances of the problem. So your final task is to go back into that worksheet.
There you
one
go.
last.
Just do your
Welcome to lesson 4.
your
the limits of
reflections,
algorithm.
and that is it.
Well,
Right? How did we get back up there?
welcome.
No. How did you create your heuristic? Did you change your heuristic after testing it? Okay, that's a sample. Takeaways, optimization, etc. Heuristics provide a good enough solution. A problem which no algorithm can be constructed that is always capable of providing a correct answer, yes or no. We will talk more about undecidable problems next class. Submit both U4 and L3 and L4. Woohoo! Sorry to run late. You are free.
Thank you.
Thank you. Have a good day.
Thank you.
Thank you. Let me know if something's not making sense. Florian, you okay? Florian? I could yell at you, Olivia, but there you go. Florian, you. All right.